Good morning, everyone, or good afternoon, everyone. I am Laure Gouba. It's my pleasure and honor to be part of the team of lecturer for the CIMPA 2021 school in Burundi. I am currently in Trieste, Italy. So let me share with you again the title of my course. So my course is about the role of group theory in coherent state and coherent state quantizations. So for the first session, I will be talking about canonical coherent state. But first, let me present some acknowledgement. I would like to thank Professor Jean Bosco Kaoya from University of Burundi in Burundi, Professor Giuseppe Dito from University of Bourgogne in France. I also thankful to the organizing committee of the school. I would like also to thank the University of Burundi in Bujumbura, Burundi, who would have hosted all of us in presence, but due to the pandemic situation, we are obliged to do online. I would like also to thank CIMPA for giving us the opportunity of this wonderful school, and also for organizing all this nice school all over the world every year. And I would like to thank the East African Institute for Fundamental Research in Kigali, Rwanda, for helping me for the video casting. So I'm thankful to all of you that are actually attending this course. A dedication goes to Professor Said Tuareg Ali. So I would like to humbly dedicate this set of lecture to the memory of Professor Said Tuareg Ali for his scientific achievement that are recognized worldwide, and the most notably are in the areas of approaches to and method of quantizations, coherent states and symmetries, wavelet analysis, connection and relationship among these topics. Many of us enjoyed his nice lectures at many scientific meetings in the world. His scientific work constitute an heritage for us. The inspiration for the preparation of the course was the work of late Professor Said Ali Tuareg on the title "An Overview of Coherent State and Coherent State Quantizations," that published in the Nankai series in Pure Applied Mathematics and Symmetries and Grouping Contemporary Physics, and that is published in 2013. And I am thankful to Professor Jean-Pierre Gazo, who provided the PDF file of the article, because I couldn't find it easily from the web. So the course has three main parts, and each part, the role of group theory is emphasized. The first sessions will be about canonical coherent states. The second session will be about the generalized coherent states. And Session 3 will be about coherent state quantizations. And for references, I would like to cite the book of Professor John Cloud and Bo Stamps on coherent states, published in 1985, the book of Pere Mulov on generalized coherent state and their application, published in 1986, the book on coherent states, wavelet, and their generalization by Professor Ali, Professor Jean-Pierre Antoine, and Professor Jean-Pierre Gazo. That is published in 2014 for the second edition. And there is also a special issue on coherent state by, again, Ali, Professor Ali, Professor Jean-Pierre Antoine, Professor Fabio Bagarello, Professor Jean-Pierre Gazo, and published in 2012. And also there's the book of Jean-Pierre Gazo on coherent states in quantum physics, published in 2009. Of course, there are many other nice books, reviews, and articles about coherent states in the literature, but I'm only able to cite what I consulted in the literature. So let me continue with the generalities about coherent state. The first example of coherent state was discovered by Schrödinger as he was interested in studying quantum state which restore the classical behavior of the position operator of the quantum system in the Heisenberg picture, that is in 1926. And as you will see in equation 1, he will set the position operator Q of t depending on the time where h is the Hamiltonian of the system. And Schrödinger understood by classical behavior that the expected value or average Q bar t of the position operator Q of t in the desired state would obey the classical equation of motion, and that is the equation 2. Schrödinger discovered the first example of coherent state pertaining to the harmonic oscillator, known universally to physicists and the prototype of every integrable model. The states are parameterized by the complex number Z satisfying the equation 3, where Q0 is the fundamental quantum length and h bar is the universal constant. Using the generating function found in the classic book of Courant and Hilbert, Schrödinger realized that a Gaussian wave function could be constructed from a particular superposition of the wave function corresponding to the discrete eigenvalues of the harmonic oscillator. Further, these new states follow the classical motion. At this time, the probability amplitude nature of the wave function was not yet known, so the complex nature of the wave function bothered Schrödinger. He wondered if perhaps only the real part of the wave function that is physical. But in any event, even though the uncertainty relation had yet to be discovered, from point of view that most closely resemble the modern minimum uncertainty method, Schrödinger had discovered the coherent state. The notion of coherent state is rooted in quantum physics and its relation to classical physics. The word coherent derives from the current language of quantum optics, coherent radiation, source emitting coherently. The term coherent was introduced by Glauber in 1963 in the field of quantum optics, and it is for a special property in quantum optics that the name coherent state was originally chosen. The importance of coherent state became widely recognized during the 1960s due to the work of Glauber, Claude, and Sudarshan. Although the name coherent state is applied to a wide class of objects, all such definitions have two basic properties in common, and which thereby may be logically termed the minimum set of requirements for a set of states to be termed coherent. In every case, the set of states refers to vectors in a Hilbert space H that is finite or countably infinite dimensional. We denote the states in question in Dirac notations like ket using the ket, where L is an element, in general multidimensional, of an appropriate labeled space D endowed with a notation of continuity in the sense of topology. More specifically, an appropriate label space is one for which every finite dimensional space is locally Euclidean. There are in essence just two properties that all coherent states share in common. The continuity, that means the vector L is a strongly continuous function of the label L. The resolution of unity or completeness, that means there exists a positive measure delta E on D such that the unit operator I admit the resolution of unity I is the integral of the projection delta I when integrated over D. The canonical coherent state, apart from their use in quantum optics, they also have found to be extremely useful in computation in atomic and molecular physics, quantum statistical mechanics, certain areas of mathematics and mathematical physics, including harmonic oscillator analysis, symplectic geometry, and quantization theory. So these are about generalities that I wanted to say about a coherent state before starting the session one that is dedicated to canonical coherent states. So let me start then with the first session. So let's say session one will be about canonical coherent state. And in session one will be organized as follows. In the first part, I will talk about the complex variable characterization of the canonical coherent state. Then for that part, I will first talk about definitions and settings. Then I will talk about the analytical properties. Then some other properties. In the second part of the first session, I will talk about the canonical coherent state, derived from Weil Heisenberg group. Okay. So in first I talk about Weil Heisenberg algebra. Then canonical coherent state, from Weil Heisenberg translation operator. Then at last I will talk about canonical coherent state from Weil Heisenberg group. Okay. So let me state that some of the demonstration will be done during tutorial session. Okay. Some of the demonstration are left for tutorial session. Okay, so this is then about what I will be saying for session 1. Okay? So let me first stop videos so that we have more space. So let us start with definition and setting. Let's start with a set of quantum state vectors zero, one, two, n. Okay. Corresponding to states zero, one, two, n exciton respectively. The Hilbert space of these states in which they form an orthogonal basis is often known as Fock space. I think you have already met a Fock space before. Let operator A dagger denote an irreducible pair of operators that satisfy the basic commutational relation A dagger is equal to 1 with the operator A apply to the vector 0, that's also called the ground state, is equal to 0. And those operators A dagger acting on the Fock state also called Fock states as follow. A operator A on vector n would give square root of n minus 1. And operator A dagger on vector n would give square root n plus 1 on vector n plus 1. And you will see that from that I can also see that the vector n plus 1 is 1 over square root n plus 1 operator A dagger over n. And if you can find by recurrence in that way that the vector n can be written as 1 over square root of factorial n A dagger power n on the ground state. And this expression is fundamental because we'll be using it also later to rewrite our coherent state. Okay, so A is the annihilation operator, and A dagger is the creation operator. Okay. The ground state is called, in some literature you can see, it's called fiducial state. Okay. You can meet most of the time ground state, but for instance, if you are reading in the book of Professor John Clouder or in his paper, you will likely meet for ground state, fiducial state. Okay, the canonical coherent state are generated by unitary transformation of the ground state. And are defined for each complex number Z by the relation Z vector is equal to the exponential of Z A dagger minus Z 8 times A applied to the fiducial state. Okay, so this is how the canonical coherent states are defined in terms of a complex variable Z. Okay. Now let me remind you the Baker Campbell Hausdorff formulas, because those formulas will be useful for technical calculation or for manipulating this expression of the canonical coherent state, because now you see that we have exponential of an expression that depend on operators. So For 2 operator AB, we have the exponential. Let me write it in blue. So the exponential A times B times exponential minus A is equal to B plus commutator A B plus 1 factorial 2 commutator A B, and we can continue with the expression by recurrence. Okay, and exponential A times exponential B is equal to exponential B times exponential A times exponential of the commutator AB. Okay, but for this we need the condition that A, B commutator with A is equal to commutator A, B is equal to 0. Okay, and we have also exponential A plus B can be split into exponential A times exponential B times exponential minus half a commutator AB. And also we need the condition AB equal AB B equal 0. Okay, and we to be able also to, if someone wants to demonstrate that, you should have in mind that exponential A can be written in terms of summation as sum n goes to 0 to infinity 1 over factorial n an. So we will be using those formulas to work on the expression of our canonical coherent state defined for each complex number z. So let's use then those formula. If we want to rewrite, we have z canonical coherent state, z defined as exponential z a dagger minus z star e on 0. If we use, we can use Rebecca-Campbell formulas, so we can rewrite that z is, so we will rewrite this expression, that is, will be exponential minus half modulus z square exponential a dagger minus a exponential z a dagger exponential minus z star a applying in 0. Okay, so let us see quickly what do we know? We know that a dagger is unit. We know that a apply to vector 0 is 0 to the background, and we know we can use the fact that exponential E, we can use it in the summation term, is sum n go to 0 to infinity 1 over factorial n minus z e power n. Okay? If you want to use that, or to make use of all these expressions, then we can rewrite our coherent state as exponential minus half z squared, and this gives us 1. So we have exponential z. I'm sorry, there is this written here. This is exponential minus half z squared times a dagger minus a. Okay, sorry. So we'll have exponential z a dagger, and then you can see that we can write that as unit minus z squared a plus times. The only contribution will be the unit here. So we have z is minus half z squared exponential z a dagger 0. So this is how we can rewrite our canonical coherent state using only the creation operator. Okay, and now we want to see how we have this expression in terms of the vector n in general instead of applying to the fundamental state 0. So I can use again the fact that exponential z a dagger is also sum 1 infinity power n. Okay. Using that, that implies that z is exponential minus half z squared sum n goes to 0 to infinity 1 over factorial n z power n a dagger power n. Okay, apply to 0. But introducing the vector n, if you remember, as square root 1 over square root factorial n a dagger power 0, then we can say that our coherent state can be rewritten as exponential minus half modulus z squared sum n goes to 0 to infinity zn over square root of n n4, n0, 1. So to summarize, you can see what do we use as formula. We can first have this as definition. Then from that, we see that we can have another way of rewriting the canonical state in terms of and if we pursue, we can also have this is exponential minus half modulus z squared, okay, sum n goes 0, infinity of zn and n goes 0, 1. Okay, so this is we can manipulate all these expression from the first definition because we use the Baker-Campbell-Hausdorff formulas and the adjoint vector. Okay, let me see the adjoint vector that I will write. This is vector as this. Okay, so this is some expressions that are equivalent, and we'll use them with respect to the context. The resolution of unit follows that we have 1 over pi integral z z d square z is equal to unit. Okay, this will be demonstrated probably during tutorial time. And if you want a hint is the following. If you want to try, use polar coordinate at an intermediate stage of the calculation. In the sense that you write z is modulus of z times I, I is a phase, or you can also if you use that, then at a certain stage of the calculation, then you may be able to show that given our coherent state, canonical coherent state Z, the relation that we call the resolution of unity holds. So the resolution of unity incorporates mathematical fact that the set of vectors Z is overcompleted in the Hilbert space. So this is about then what I call settings and definitions. Now let us see the analytical property of the canonical coherent state. Then 1b, analytical properties of the canonical coherent states. Let's consider an arbitrary vector that I denote phi in the Fock space. From the expression Z is exponential minus modulus Z squared over 2, sum n goes to 0 to infinity, Z power n square root n factorial, n we have the overlap phi Z or scalar product is equal to exponential minus modulus Z squared over 2, sum n goes to 0 to infinity, Z power n over square root n factorial overlap phi n. Okay, if we set f of z, function f of z is equal to sum n goes to 0 to infinity, Zn square root n phi n, then we can say that the overlap phi z is equal to exponential minus z modulus square over 2 of this function f of z. Okay, where f is an entire analytic function in the complex variable set. So this is one analytical property of the canonical coherent state. Another is that it follows that the overlap Z2, Z1 is equal to exponential minus half Z2 square plus Z2 star Z1 half Z1 square. Okay. So this expression we can show it quickly. We have vector Z1 is, let us use now this expression. Diagram Z. We have, if I write Z2 as exponential minus half modulus Z2 square 0 exponential Z2 star E. Okay, if I have the vector Z1 and the adjoint vector Z2, so the overlap Z1, this is Z2, Z1 would be equal to M over formulation minus half Z2 square Z2 star A minus half Z1 square exponential Z1 E dagger 0. Okay, you can see that I can pull those first part exponential minus half Z2 square exponential minus half Z2 modulus Z1 square, then I remain with 0 exponential Z2 star E exponential Z1 E dagger and apply to fundamental state 0. Now we can make use again the Baker-Campbell-Hausdorff formula. If we use the Baker-Campbell-Hausdorff formula, then we can show that this is a straightforward exponential Z2 A exponential E dagger can be again rewritten as exponential Z1 E dagger exponential Z2 star E times exponential Z2 E Z1 E dagger, and we know well what will give this expression, and that gives us exponential Z1 E dagger exponential Z star E times the product exponential Z2 star Z1. Okay. Now, if we use if we use this later formula, then we can now calculate our overlap Z2 Z1 as follow. That will give us exponential minus half Z2 square exponential minus half Z1 modulus square exponential Z2 star Z1. Then I remain with vector 0 adjoint exponential Z1 A dagger exponential Z2 star A applied to fundamental state. Okay, and this expression, we can expand this expression as follow. I can check this. Then using the summation form of the exponential Z1A dagger, I can start. It will be 1 plus Z1A dagger plus A infinite. Then times, I use the expansion of exponential Z2 star A. Then I have 1 plus Z2 star A plus, okay, and that apply to 0. And you will see that for this, the only contribution I will have is the fact that I have in each product part the operator unit. So the overall here will be giving me this, that is 1. Okay, this is auto normalized. So I will remain then with the overlap Z2 Z1 can be then be shown that is equal to minus half Z2 modulus square plus product Z2 star Z1 minus half Z1, and this is a continuous function. This is a non-vanishing because it will never vanish. You know, we can, in a certain, if we continue the calculations, we can have an expression in terms of modulus of Z1, Z2, and probably if this modulus goes to 0, it can approach 0, but it's obviously a non-vanishing continuous function of the variable Z1 and Z2. Okay, so I also state that as an analytical property of the canonical coherent states. Now, let's see the property of Z of this coherent state. There are other more nice properties. So in 1C, then properties of the canonical coherent state. Okay. The operator, let me rewrite this. I haven't said that, but I should say that. The operator that we set dz is equal to exponential z e dagger minus z conjugate a is called displacement operator. Okay, so if you want, you can say that the way we define the canonical coherent state here, it is states defined by applying the displacement operator on the fiducial state there. Okay. So if we have then displacement operator, one can show that if we take the adjoint of dagger of the displacement operator times A times the displacement operator dz, okay, one can show that this is equal to A plus Z. One can equally show that the adjoint D times the dagger dz is equal to A dagger plus conjugate of Z. Then for each complex Z, the coherent state is and eigenstate of the annihilation operator. A with eigenvalue Z, in the sense that we have A applied to canonical coherent state Z is equal to Z, Z. And this property make also the canonical coherent state called Glauber state. So you can see that the ground state is a canonical coherent state. The ground state is a canonical coherent state, okay, as we have A 0 is 0, 0 is equal to 0. So it follows then that we have also Z A Z is equal to Z. This is immediate from the property if you see the property of a global state. So Z is interpreted as the mean value of A in the coherent state Z. Okay, so each state Z satisfies Z A dagger A Z is modulus Z square. So later on, or I think in my presentation, you have already heard about minimum in certain state. Okay, so it means they saturate the uncertainties. So it means that the canonical coherent state Z, these are properties, is a minimum uncertainty states as defined in the slide presentation. We can also demonstrate that during tutorial session. Yeah, session. Okay, so these are then for the canonical coherent states, as we have defined some of properties that are very useful, that, as I said, you may be using it or you may need it depending on the context. Now, this is the end with the first part. That is first part that I call the complex variable characterization of the canonical coherent state. Now, let's see how we derive canonical coherent states from the Weil-Heisenberg algebra and moreover from the Weil-Heisenberg group. So, and this is the second part of the lecture of session 1. So, canonical coherent state derives from the Weil-Heisenberg algebra and the Weil-Heisenberg group. Okay. So, but first of all, I would like to do some to recall basics of quantum mechanics. Okay. Let's first recall following basics of quantum mechanics. Okay. So in quantum mechanics, a particle M particle in n dimension can be described with a wave function in L2 Rn, and that is the Hilbert space of square interval function. The position and the momentum operator of the particle are described as follows. They are self-adjoint operator, and I can then choose, since we are in Rn, as Q1, Q2, Qn, where an operator Qg goes from L2 Rn to L2 Rn, where Qj apply in a function f is equal to, on a vector f, is equal to the argument xg minus f. And the momentum operator is P1, P2, Pn, such that if we have an element pk, this goes from L2 Rn, L2 Rn, Pk applied to vector f is minus I h bar partial derivative f with respect to the argument xt. Okay? And the operator QGPK they satisfy here the commutation relation QG operator PK operator is equal to I H bar delta G K. Okay? On the domain these two at the intersection D. Okay? Then of course J goes 1 N and K also goes 1 N. So this is just to recall that we will be using that for our value Heisenberg representations. Okay? After we have said few words about some recall in quantum mechanics, now let's see how we define the Weil Heisenberg algebra. Let's consider in n dimension the Weil Heisenberg algebra that I denote n as the 2n plus 1 dimensional real vector space generated by elements I P1. Let me write in the next line. I P1, P2, Pn, Q1, Q2, Qn. Okay? Satisfying the commutation relation Q, J, Qk is equal to 0 and Pj, Pk is also equal to 0. The element I, Qg is equal to 0 and also the element I, Pk. Okay? And the commutator of the element QG PK is delta G K H bar times the element E. Okay. And that holds for G K in 1 N. Okay. Now, if we consider now a set of coordinate Z is P2 that belong to Rn cos Rn and T that is R, then we can write any element of the algebra, of the Veil Heisenberg algebra, as U is equal to T over 2h bar times the element I plus 1 over h bar times P, the dot product P times Q minus the dot product Q times P, where dot products are defined as P dot Q is defined as the summation J goes to 1 to N P J Q G and Q dot P is the summation J goes 1 to N of Q G P J. Okay, so this is how we defined Heisenberg algebra and how an element of the Heisenberg algebra can be written. Okay. Once we have defined the Heisenberg algebra, let's see how we set the Lie algebra representation. A Lie algebra representation of the Weil Heisenberg algebra can be formed by setting by letting I, element I goes to minus I times unit operator. The element Q goes to I operator Q, like the position operator. The element P goes to I times operator P. Okay. Of course, we have Q operator is like we have said from the recall of quantum mechanics, Q1, Qn, P, Q1, Qn. Okay. So, which is called Schrödinger representation. And every element U of the Weil-Heisenberg algebra correspond to an operator U equals to minus I T over 2h bar unit plus I h bar P times Q dot minus Q times P dot P hat. Okay, where of course the dot product P dot Q hat is the sum J goes 1 to N Pj Qj and Q dot P hat is the sum J goes 1 to N Qj Pj. Okay. So this is the Schrödinger representation, also called the Lie algebra representation of the Heisenberg algebra. Okay, so once we have that, now we would like to define the Weil-Heisenberg translation operators. Okay. The Weil-Heisenberg translation operator. Let's consider the position and momentum operators to P on the intersection of the domain of Q and P. We define the operator LZ is equal to P dot product Q minus Q dot product P for every Z in R plus R. Of course, I already says where the P dot product Q is some J goes 1 to N Pj to operator J, a Q dot P is some K goes 1 to N Qk P dot K. Okay. So with respect to that, we can say that in the Schrödinger representation, the operator U can be written as 1 over P 2 minus 2 P can be written as U is equal to minus I T over 2H bar operator unit plus I over H bar operator LZ. Okay, so this is about how we define the Weil-Heisenberg translation operator. Since the position and momentum operator Q P are self-adjoint, operators L, the translation operator, is self-adjoint. and hence the generator of a unitary operator that we call TZ, called the Weil-Heisenberg translation operator. So it's defined as T Z is equal to exponential I H bar times LZ. You can see that in my previously here we defined the operator L of Z at the intersection of the domain of Q on P in that way. And we see that in the Schrödinger representation, each element of the Heisenberg algebra can be represented in terms of the operator L of Z. Then also we have that we defined the Weil-Heisenberg translation operator as the exponential of I over h bar of the operator L of Z, and it's called translation operator. It is referred to as a translation operator because it translates a state in phase space by a shift Z to P indeed. Indeed, it is possible to show that for a vector F the Hilbert space L2 and a complex number Z that we represent as QP Rn. We have T Z translation operator apply to the vector F taking on X is equal to the exponential minus I 2h bar Q dot P, coordinate Q dot P P exponential I h bar over h bar x dot p times the function of x minus. This can be shown, and this will be demonstrated in the tutorial. So this is then about the Weil-Heisenberg translation operator, and this is an operator that translates a state in a phase space by a shift. And we will see the property of and the use of this operator. Now, the canonical coherent state can be defined by shifting the ground state zero round in phase space by the translation operator Tz. Okay, so we have Z is equal to Tz applied to the ground state or fiducial state. So it means that the canonical coherent state can be then written as exponential I over h bar times p dot q minus q dot p. So this is how we define again canonical coherent state using the Weil-Heisenberg algebra. Because you see that from the Weil-Heisenberg algebra representation, that is showing a representation, we can define the translation operator T of Z, and shifting around the ground state zero in phase space by the translation operator, we can generate the canonical coherent state. Of course, you know that Z is Q, P, A, that belong to R. Okay, so with that, we can say that all canonical coherent state corresponds to the ground state shifted by some while Heisenberg algebra. For example, we have seen previously that the ground state of the harmonic oscillator is a coherent state. In the sense that we have the annihilation operator applied to the ground state is 0 times the ground state. Okay? So we can obtain all canonical coherent state by shifting this ground state around in phase space. Okay. So let's see now the last part that is about the Weil-Heisenberg group and how we defined canonical coherent states. Okay. Weil-Heisenberg group and canonical coherent states. Okay. The Weil-Heisenberg group that I will denote here with capital H, capital W, capital H, N is the simply connected Lie group connected Lie group associated to the Weil-Heisenberg algebra by the exponential map. Using the coordinate system, Z is equal to PQ T on R, okay, like in the algebra N, the group operation on the Heisenberg group can be written as T Z T bar Z bar is equal to T plus T bar plus sigma Z Z bar Z plus Z bar, where sigma Z Z bar is equal to Q P bar dot minus P Q bar. So this is the group operation on the Heisenberg, on the Weil-Heisenberg group. Once we have that, let's see now the Schrödinger representation. The Schrödinger representation on the Weil-Heisenberg algebra lift to a unitary irreducible representation on the group is defined by rho Tz is exponential of the operator of U. Remember that the operator U was the Schrödinger representation of any element of the Bell-Heisenberg algebra. Then here we defined rho Tz as the exponential of U, that is rho Tz is equal to the exponential of minus IT divided by 2h bar times operator unit, okay, times the exponential of I h bar Lz. Okay? But you know well that this is the translation operator. So rho Tz is exponential minus IT 2h bar times the translation. So in that sense, the canonical coherent state corresponds to the set of states psi is equal to rho g of psi not g in the Heisenberg group 1. Okay. That means the canonical coherent state corresponds to element of the Weil Heisenberg group acting on the ground state through the Schrödinger representation. So this is how one can define the canonical coherent state from the Weil-Heisenberg group. And you have seen also that from the Weil-Heisenberg algebra, defining the Weil-Heisenberg translation operator, we can also define the canonical coherent state. So this is, let's say, the end for session 1. Okay. So sharing. So I hope you enjoy it, and see you for the next session. That is session 2 about a generalized coherent state.